Hey physics students, so in Unit 1 we talked about measurement, and we finished Unit 1. We talked about measurement, we've talked about significant digits, and we've talked about how we, the metric system, and now we're going to move into Unit 2. Unit 2 is about what we call motion, right? Unit 2 is about what's called linear motion or one-dimensional motion. Basically, it's going to be about things moving in a straight line. Right? They might be speeding up, they might be slowing down, they might be stopped, they might be going backwards, but things moving along a straight line. And so today what we're going to do is we're going to talk about some of the basic parts of motion. We're going to talk about position and time, and then we'll end up talking about velocity towards the end of the lesson. So our target that we want to be able to accomplish here, we want to be able to describe the relationship between displacement, velocity, acceleration, and time. So let's go ahead and let's talk about some of those things. How do I talk about something's motion, right? Let's think about a ball rolling along the floor, right? Maybe it starts out over here, and then later it's over here, and then later it's over here, and then over here. That's pretty bad. Try to make it a little bit more straight. So here, and then later it's here, and then later it's here, and then later it's here. That's a little bit more straight. Okay. So I have a ball rolling along the floor. Starts out here, and then it's here, and then it's here, and then it's here. How do I talk about its motion? Right, well, usually what we'll do is we'll say that one particular place is 0. Okay, so let's call that place 0. And what we'll do is we'll make kind of like a number line, like you might see in math, right? But our number line is really kind of more intuitive because it's basically just like a ruler. Okay, so let's say here is 0, and then let's make a little underline. And I don't know, maybe here it's at, how far is it gone? Maybe it's gone 2 meters. Maybe a little bit later here, now here it's at 4 meters. And then later on, maybe over here, maybe it's at 6 meters. Okay, so one of the key ways that we're going to talk about the motion of an object is where it is. How do we determine where it is? We need to call a place 0, and then say how far the thing is from 0. Right? Does it matter where 0 is? It doesn't matter. I could have said this was 0. And then when it was over here, it was here before it was here. So maybe this was negative 2 meters. And this was negative 4 meters. And this is a negative 6. It doesn't matter where 0 is. You can put 0 anywhere. We could put 0 in the middle. We could say this was 0. And then this is at 2 meters. And this is at 4 meters. And this was negative 2 meters. It doesn't matter where 0 is. 0 is just wherever you called 0, right? It's wherever we start measuring. So when we talk about where the object is, we call that the object's position. Okay? And when we work with our physics mathematically, we'll use a variable for position. We'll use the variable x. When you see the variable x, that stands for the object's position, right? And when we measure position, we usually measure things in what are called in a standard unit. When we're going to do math in physics, our quantities have to be in a standard unit. We can measure position in centimeters. We can measure it in feet. We can measure it in miles. But the standard unit for measuring a position is the meter, right? So whenever we do math, we have to have our measurement in meters. Okay? So position, its variable is x, and its standard unit is meters. That's going to be important for us to know. Okay. Now, what's going to be more important to understand than position is what's called the change in position. Okay, so let's get there in a second here. Okay, my ball that was rolling across the floor started at 0. Okay, that place where it started, we're going to call the initial position. Okay, so this was its initial position, and we're going to use a variable to refer to the initial position, x with the subscript I, right? X with the subscript I. The subscript I tells me it was the initial position, right? X for position, I for initial. Okay, so I would say the initial position is 0, and that ball is going to move along, and it's going to go somewhere else. And the place where I stop looking at it, whatever where it ends, we call its final position, right? Maybe I stopped looking at it here. Maybe it kept going, but this is where I'm done being interested in it. We'll call this the final position. And for final position, we use x with the subscript f, x sub f. X subscript f. For final position, x for position and f for final, right? Final position. So my ball moved from the initial position of 0 to the final position of 4. Forget about that. That's unimportant for us right now. Okay, so how far did my ball move? All right. When we talk about how far something moved, what we do is we call it the displacement. For the displacement is basically how far is it from where it started. Okay. It's not exactly the same as how far did it go, right? How far did it go depends on the path it took. We'll talk about that in a second. But this is what's called the displacement. It's how far is it from where it started. So how far is my ball from where it started? It's a pretty easy problem to figure out. Most of you can probably see it's 4 meters from where it started, right? What if I had called a different place 0? It's 4 meters away, right? What if I had called this one 0? Then this one would be 2 meters. And this one would be negative 2 meters. How far is it from where it started? Well, it's still 4, right? 2 minus negative 2 is 4, right? And so that tells us how we can figure out displacement. How far is it from where it started? We can figure out the displacement by taking the final position and subtracting the initial position, okay? For displacement, we're going to use a variable called delta x, okay? You can see the triangle is the Greek letter delta. And delta means change. We're going to see the delta quite a bit throughout physics, okay? Delta means the change. So when I see delta x, delta means change, x for position. So delta x is the change in position, okay? Delta x is the change in position, which is the displacement. Let me draw my x a little bit nicer. Delta x is the change in position. It's the displacement. It's how far is it from where it started. And I can easily calculate that by taking the final position of the object and subtracting the initial position of the object. So delta x equals x sub f minus x sub I. It looks fairly complicated, but it's not. It's really simple. It's basically, if you want to know how far it is from where it started, take its final position and subtract its initial position. The other really prime component of an object's motion for us to understand is time. Okay? Time goes by, right? Time, it flows, it goes by, you can't stop time, time can't go backwards, it's always moving, right? So usually, with an object's motion, at some point we'll say the time is 0. Time is 0, that's when we started observing it, right? And let's say, here, with my rolling ball, right here at this position, time is 0. 0 seconds. Okay? And when we talk about time, we're going to use a lowercase t as the variable, lowercase t for time. Okay? And just like with position, there is an initial time and a final time. So if I started observing my ball here, I would say that the initial time is 0. So we can use a t with a little subscript I for the initial time. And then later on, let's say, I don't know, maybe when the ball was here, 1 second had passed. So now, we got 1 second. And then when it gets here, 2 seconds have passed. So 2 seconds. And this is when we stopped observing it, right? So we could call this the final time, right? And we can use a t with a subscript f. T sub f for the final time. So we say the final time is 2 seconds, right? So if the initial time was 0 and the final time was 2 seconds, how much time has gone by? Well, it's pretty obviously 2 seconds, right? All you have to do is take the final time and subtract the initial time. So just like with the position, if you remember, with the position, you find the change in position, the displacement, by doing the final position minus the initial position. And the same thing with time. In fact, how much time has gone by. Sometimes people might just call it time. Sometimes people might call it elapsed time. But it is how much time has gone by. We say delta t, the change in time. How much time has gone by. We can take the final time minus the initial time. So the two equations, they look very, very much the same, right? To find the change in position, take the final position minus the initial position. To find the change in time, take the final time minus the initial time. Pretty simple, huh? Okay, so now for my rolling ball, I've made a little chart here that tells me the position and the time of the ball at various spots, right? So when the ball was at position 0, 0 seconds had gone by. When the ball was at position 2 meters, 1 second had gone by, and so forth, right? So this is the same ball we were just talking about in the picture that I had drawn. Now, a very convenient way to look at data concerning a moving object is with a graph, okay? We can very easily make what's called a position versus time graph, okay? Position versus time graph is gonna have the position on the y-axis of the graph and the time on the x-axis of the graph. So let's make a little graph here. We could use a graphing program. I'm just going to draw one by hand. Okay. So here I have my y-axis, and here I have my x-axis, and you can make the negative portions of the axis as well. I'm just going to use the positive parts right here. Okay. But the negative portions can also be there. Okay. So over here, the y-axis, I'm going to put the position. And I've measured these in meters, so I'm going to put meters right there so we know these numbers are in meters. And then along the x-axis, I'm going to have time. And we've measured that in seconds, so I'm going to put seconds right there so we know it's measured in seconds. Okay, I'm going to number my axis. So looking at my times, it's going to be convenient to just number 1, 2, 3. 1, 2, 3. And then looking at my x-axis, I've got, 2, 4, 6. So I'm going to number 1, 2, 3, 4, 5, 6. So here's 2, here's 4, 6. Okay. Now let's put some points on the graph, right? When my ball was at 0 meters, it was at 0 seconds. So that's right here at the origin. When my ball was at 2 meters, when the position was 2 meters, the time was 1 second. So put a point right there. When the ball was at 4 meters, the time was 2 seconds. 4 meters, 2 seconds. And when the ball was at 6 meters, it was 3 seconds. Right, so let's put that point right here. And there we have a graph of the motion of my ball. Right? And this graph can tell us some important things. It can tell us some useful things, right? If I connect my lines, I connect my points with a line. Draw as straight as I can. There we go. Okay. This line tells us some things about the motion of the ball. Okay. If you think about it, these are just the places I measured the ball. Was the ball at some point between 2 and 4? Was it at some point at 3 meters? Yeah, it was, right? And I can look at my graph and I can find 3 meters here, and I can see that at this time, the ball was at 3 meters, right? So there's 3 meters, down, and I can tell at about 1.5 seconds, it was at 3 meters, right? So I can find parts of the motion where I didn't take data, right? But there's also another really important thing about the graph that's going to tell us a really important aspect of the ball's motion. And that's the slope of this line. The slope of this line is a very important number. The slope of this line is the velocity of the ball. Okay, so let's find the slope of this line. Slope, if you remember, we can find the slope of a line using rise over run. Okay, so let's just take 2 points on my graph. Let's take this point and let's take, say, this point. It rises how far? It rises 6 meters and it runs 3 seconds, right? So 6 meters over 3 seconds. 6 over 3 is 2. And what are my units going to look like? I've got meters over seconds. So I'm going to call that meters per second. So the slope of this line is 2 meters per second. That's the velocity. That tells me how fast is the ball moving. If I have a straight line, like this is a straight line, I know that my ball was going at what we call a constant velocity. It means the velocity wasn't changing. If I have a line that looks different, let's say I have a line that's curved instead. What if my line goes like that? What does this tell me about the ball's motion? Well, here, the line is not very slopey down here. But when we get up here, we get a much larger slope, right? What this tells me is that in this part of the ball's motion, its velocity was lower, and then here its velocity was higher. So a ball doing this is speeding up. What about one that goes like this? What's this ball doing? Well, you can see here we have a high slope, which means it's moving fast. And then what happens is the slope gets lower. So with a low slope, it's moving slow. So what happened to this ball? It was moving fast, and then it's moving slow. This ball is slowing down, right? But if I have a straight line, whether it's like this, that means we're moving at a constant velocity, right? Kind of a special case of that. What if it's like so? If you have a flat line like that, what does that mean? What's the slope of a flat line? It's 0. So what's the velocity of this ball? It's 0. So how is this ball moving? It's not, right? Its velocity is 0. It's not moving. You notice its position doesn't change, right? It's just 6 the whole time. Okay, so let's think about our graph real quick here, okay? We had position on the y-axis and we had time on the x-axis. Now how do we find the slope of the line? We find the slope by doing the rise over the run. Okay, now follow me here. Let's think about what the rise is. The rise is how far it goes along the y-axis, right? It's how far you rise. Okay. Well, what's along the y-axis? It's the position, right? So if the rise is how much the y-axis changed, then what we're talking about here is how much the position changed. And we talked about just a minute ago, we have a variable for the change in position. We called it the displacement. This rise is the displacement. And we said we're going to use the variable delta x. Okay. What about the run? What's the run? Run is the change along what's on the x-axis, right? What do we have here on the x-axis is time. So what we're talking about with run is how much does the time change. And we said a minute ago we have a variable for the change in time. We said it's going to be delta t. So rise is delta x, run is delta t. So rise over run is delta x over delta t. You remember the slope we said is the velocity. And we're going to use a variable lowercase v for the velocity. Okay, so here now we have an equation. We can calculate the velocity of an object. We don't have to make the graph to calculate the velocity. The velocity is the displacement divided by the time. So what if my ball traveled 6 meters in 3 seconds? That's all I know. It traveled 6 meters in 3 seconds. Okay. Well, I know delta x. It told me it traveled 3 meters. Delta x is 3 meters. I know how much time has passed. It told me, I said 6 meters, didn't I? 6 meters. And the amount of time that passed was 3 seconds, we said, right? So I know the change in time, delta t. 3 seconds. Can I tell how fast the ball is moving without making a graph? I sure can. I just put these numbers into the equation. So the velocity, delta x is 6 meters, delta t is 3 seconds. And then we just divide them. So 6 divided by 3 is 2. And what are my units? I've got meters on top and seconds on bottom. That's meters per second. So I can calculate the velocity of an object without making a graph. Okay, here I've drawn a graph. Let's talk about the motion of this graph, right? What does this graph tell us about the motion of this particular object? Okay. What about at this beginning section here? You can see this is the first 2 seconds of its motion. The line is flat. What does that tell us about its motion? Well, it tells us that it's not moving during that time, right? Its position is 0, and 2 seconds later, its position is still 0. The slope of that flat line is 0, so its velocity is 0. It's not moving, right? What happens then? You can see the line goes down into the negatives. What does that mean? That means, the line is going down. This object is moving backwards. It's moving in the negative direction. Oftentimes, we'll say one direction is positive and the other direction is negative, right? I mean, really, which way is forward and which way is backward is kind of arbitrary. It doesn't really matter, but, usually we'll say one particular direction, usually either to the right or up, is positive, and the other direction, to the left or down, is negative, right? It's arbitrary, but you just define one direction as positive and the other direction is negative. So here, my object is moving in the negative direction. How far does it move? Well, it moves down to, 3 meters in the negative direction. And it takes, what time is it there? We said 5 seconds. So from 2 seconds to 5 seconds, it was moving in the negative direction. It moved 3 meters in the negative direction. If you want, you can find its velocity. It moved 3 meters in 3 seconds. So it was 1 meter per second in the negative direction. We might say it was negative 1 meters per second. What happens after that? What happens right here is the object changes direction. Does it stop? No. It just goes from moving backwards to moving forwards. Okay? And you can see it's a pretty slopey line there, so we could say it was moving pretty fast there. Okay? And it moves right here. It moves past the place where it started. The place it started was 0. Here it's at 0 again. So it's moving past, so it goes backwards, and then it goes forwards. It goes past the place that it started and continues moving for another couple of meters there. So it moves from -3 to 2 meters. So it moved 5 meters. In how much time? Well, it took it from 5 seconds to 7 seconds. So in 2 seconds, it moved 5 meters. So 5 over 2 is 2.5 meters per second in the forward direction. Okay? What happened then? A flat line, it stopped. Right? So it moved forward to 2 meters and then stopped. And then what happened? Well, it started moving in the negative direction again, went back past the place where it started, moved way down to -6 meters, and then changed direction again. Went forward, didn't quite get back to where it started, and then stopped for a couple of seconds. And then it moved forward to the place where it started, and then it stopped. So we can take a look at a graph. We can see exactly how this object moved. We don't even have to know what the object is. It could be a ball, it could be a car, it could be an airplane, it could be a asteroid, it could be anything. Who knows? It doesn't matter. It's our object. Okay, this looks somewhat more complex. Let's talk about this a little bit. When we have lines on the graph that are not straight lines, we can still say something about the motion, but we can't calculate what its velocity is. So look at my graph here. You see my object starts out with a curvy line here, right? I can say something about its motion. It started out moving slowly, and then it sped up and was moving more quickly. I can't tell you how fast it was going though, because its velocity was changing, right? If it was changing, it wasn't always the same, so I can't tell you what it was. But I can tell you that right here, it stopped because we have a flat line. And then we have a straight line, right? Here, we can tell you how fast it was going. All we have to do is find the slope of that line. If I had some numbers on here, we'd calculate the slope. And then after that, you can see a line that jumps up real quick and then evens off, right? So this tells me it started out, again, moving fast, and then slowed down, right? Can I tell you how fast it was going there? No, because its velocity was changing, right? So there isn't like one number for how fast it was going. So I can't tell you what its velocity was because it didn't have just one velocity. It changed, right? But I can tell you it started out moving quickly and slowed down. So with a curve, we can say whether it was speeding up or slowing down, but we can't really say what its velocity was. Not unless we know a little bit more math. All right, so we've talked about position and time. We've talked about how we measure these things. We've talked about displacement. We've made some position versus time graphs, and we looked at the slope of those graphs, and we saw that the slope of those graphs is the velocity of our object. So hopefully that helps us to be able to describe the relationships between position, time, velocity, and acceleration. And next time, we'll talk a little bit more about velocity, and we'll make some velocity versus time graphs, and we'll talk about what acceleration is. So until then, take it easy.